So this is a revision video about chirality for A2 organic chemistry. So during your AS studies, you would have come across structural isomerism and stereoisomerism. This is another form, but it's called optical isomerism. For this, you will need something called a chiral center. Now, for a compound to have a chiral center, okay, chiral centers only exist if you have 4 different groups attached to a carbon atom. So you need 4 different groups attached to a central carbon atom in order to have a chiral center. So let's have a look at an example of this. So if we've got here a carbon atom with an alcohol group, we could then have C2H5. Then we could maybe have an NH2 group coming off, so an amine. So if it's a solid wedge like this one, it means it's coming towards us, it's coming out of the paper. And if you've got a dashed wedge, it means it's going backwards. So imagine these lines as being in the plane of the paper. This one is going backwards, the dashed one, and the solid wedge is coming forward. So it gives you a nice 3D view. So each of these are a different group. Here we've got an ethyl group, here we've got an OH, here we've got a hydrogen, and here we've got an NH2. So we've got our 4 different groups around it. Imagine if I now had a mirror plane. So I'm going to draw the mirror image of this one. So the hydrogen is going to be going back. Then I'm still going to have the NH2 coming forwards. I'm then going to have C2H5 and I'm going to have OH. So these are mirror images of each other. These are mirror structures. They're referred to as non-superimposable. So one way to think about it is like a hand. Okay, so these would be mirror images of each other. However, if we tried to put them on top of each other, they wouldn't match. So that's what we mean by non-superimposable. So the molecule on the left here, if we put that, lined it up in front of the other one, it wouldn't match. Mods are a really good tool for you to have a play yourself and realise that even no matter how you rotate them round, once you've set them up as mirror images of each other, you can never get them to superimpose on top of each other. So these are non-superimposable. So they are optical isomers. Another name for them is they are called enantiomers. So this is an enantiomer of this. So you quite often find them in things like sugars, amino acids, nucleic acids. There's lots of compounds in nature that have chiral centers in them. So especially those of you that are studying biology, why don't you look at your amino acids and look at how you can draw those with the different optical isomers. So looking at these chemically, these would react in exactly the same way as each other. So with optical isomers, they will react in exactly the same way. The only thing that is different is they will interact with biological systems differently. So those that are doing biology, if you think about things like enzymes and things like lock and key sites, this one would interact differently than this one with the lock and key example. The other thing is if you have a plane of polarized light, one will rotate the light in a different way than the other. So they react in exactly the same way, but they interact with biological systems differently, and they will rotate a plane of polarized light differently. So if it rotates the light in a clockwise fashion, we would refer to it as the plus enantiomer. So that's if it is clockwise. It's the negative. It's a negative enantiomer if it goes in an anti-clockwise rotation. So that's something to bear in mind when you're looking at applying the keywords to exam questions. So if we look at an example, let's see if we can identify how many chiral centers there are. So as well as being able to draw them and know that they're non-superimposable, and know about the fact that they react the same, but they interact differently with biological substances, and they rotate the plane of polarized light differently. The other thing you need to be able to do is within an organic molecule, you will have to be able to spot which are the chiral centers, so how many there are, and sometimes they get you to put a little star next to the carbon atoms that have chiral centers to check your understanding of where the chiral centers are. So let's draw an organic molecule and see if we can figure out how many chiral centers there are in it. So if I've got something like, so here I've got a benzene ring, CH2, going to a carbon with another benzene ring. Then I've got an ester, then with a CH2, CH3. Then up from here I've got another carbon atom with a methyl group, a hydrogen, CH2, and a nitrogen with two methyl groups coming off it. So you might have a structure like this, and you might be told how many chiral centers there are. So you might be asked how many chiral centers there are in this molecule, and draw a star next to the carbon atoms with chiral centers. With your benzene ring, because there has to be 4 different groups, you can't have a chiral center directly on a benzene ring. So neither of these benzene rings will have chiral centers. The carbon here cannot be a chiral center because 2 of the groups coming off it are hydrogen. Remember, you need 4 different groups. This carbon here, we've got a CH2 coming off this way. We've then got a carbon with some other groups coming off it. So that branch is different from this one. Here we've got an oxygen coming off, and here we've got a benzene. So this one would be a chiral center. Okay, if we go along here, the carbon on a carbonyl cannot be a chiral center because 2 of the bonds are to oxygen, and again you need 4 different groups. So it cannot be a carbonyl carbon. And again, this carbon, 2 of the groups are hydrogen, so again 4, you need different. Here, that carbon, 3 of them are hydrogen. So we know no chiral centers here. This one, this group coming off it is different from a methyl, which is different from a hydrogen, which is different than this group. So this one is a chiral center. A methyl group can't be a chiral center. And again here, two of the groups coming off it are hydrogen. The nitrogen is not a chiral center. And then the methyls can't either. So in this molecule, there are just 2 chiral centers, and they are the ones highlighted. You can get other examples. So let me just take this one off the stand. So if we go over to my example here, this is cholesterol. If we look through this one, we've got, so this one here is a chiral center because we've got the OH coming off it and this group going around here is different than this way. You may think you've got a CH2 group initially coming off it, but if you imagine you're walking around the molecule, this the next carbon along is different than the next carbon along here. So this one is a chiral center. Okay. Here we have a chiral center here, because these 4 groups are different from each other. We have a chiral center here, another one here, another one there, another one there, one here, usually people miss that one, and another one here. So again, have a look at that structure and think, can I label all of those chiral centers confidently? If you can for this, then you'll be fine. Best of luck with chiral centers.